So far, we did energy balances and the formulas that let you calculate some things. I want to give you an example, getting a little bit into the physics, something cool. And this is a story. I want to discuss boundary layer. That sounds scary, right? But let me tell you this story. I understand you did with Ying this example in which you calculated how your metabolic rate balances with your heat losses by convection, right? Isn't that amazing that the same thing that says in the wrapper of what you eat, right? You need more or less 2,000 calories a day, is the amount of energy you're going to lose through your skin. It's no coincidence, right? It's awesome. So let's take it one notch up, right? We already said that we're losing energy. In this case, I'm quiet by natural convection. Natural means just like the hot air rises and takes some heat out, right? And let me tell you something about the physics. How does it work? The air moves around you, or the water moves around you, right? And something that this guy Prandtl, just about 100 years ago, discovered is that the air away from you, or the water away from you, is moving fast, and viscosity plays very little role. But right on your surface, it gets stuck, right? And when we discuss convection, I'm going to show you videos of boundary layers. But the bottom line is this. There is a layer of air that is stuck to your skin. If you're swimming, there's a layer of water that is stuck to your skin. Stuck, right? You can do the equations of fluid mechanics and everything. So when we talk about convection, in reality, and this is super important because we're going to use it later, but when I said convection doesn't exist, right, what really exists is conduction through this layer that is stuck to your body, all right? So my mission to you guys is this. If you believe me this, and I'll show you videos and much more stuff, if you believe me that the convection comes from a thin layer of this fluid that got stuck on our skin, I would like you to tell me what is the thickness of that layer. How would you go about? What is the thickness of the layer, right, of the air layer that is stuck on my skin, such that I have 10 watts per square meter Kelvin in convection? How would you go about that? The reason I lose 10 watts per square Kelvin and not more is because that layer. If you go swimming, you're going to lose a whole lot more. You're going to lose 1,000 watts per square meter Kelvin. That's why you don't swim at 20 degrees. You're going to freeze, right? Your metabolic heat, the 2,000 calories, they don't make up for how much you lose through your skin. So understanding that we have this layer, you can be naked, but you're not naked. You have an invisible jacket of air. Now, so now, what is the thickness of the jacket? I like what you suggested, Fourier's law, right? And so if it is a thin layer, right? And we elaborated on Fourier's law, right? If it is a thin layer, can I use the plane wall learning we have? Can I say that the air around my finger is a plane wall? Well, that depends if it is thin or not, right? So let me teach you something that is super cool. It's called self-consistency. Let's assume it is very thin. Let's come up with all our story and then verify. If I predict that the layer is 1 meter thick, it didn't work, right? But if I predict that the layer was 0.5 millimeter thick, I'm okay with it, right? Convection is conduction through boundary layer. I'm going to start by assuming a boundary layer is thin. Two things. Number one, it is thin, so I know the end of the story. But the other thing is, if I assume it's thin, I can do lots of cool things. So it is convenient to assume it's thin, even if you didn't know the end of the story, right? So if the boundary layer is thin, we can use this plane wall. And Fourier's law told us that the resistance of the plane wall is L over K. What would L be in this case? It's the thickness of the layer, right? That's what it is. I don't know what the number, but what is K? Thermal conductivity of what? My finger? Of the air, right? Or water, whatever it is, of the fluid. So for air, right, we have K is more or less 0.03 watts per meter Kelvin. That's from the book. Okay, so that is for conduction. But we said this is, in reality, convection is a shorthand for this conduction, right? This came from Fourier's law. The resistance of conduction should be the same as resistance of convection, right? Because what I'm saying here is we call it convection, but in reality it's conduction. It's the same thing. We take a shorthand, a shortcut, and we call it convection. How did I calculate the resistance per unit area of convection? 1 over H. What is H for still air? I've been saying it a million times now. More or less 10, right? Still air means natural convection, right? I said reality is the resistance preventing me from freezing to death is L over K. And we have tabulated it as convection. This invention, amazing invention that is so practical, but in reality is nothing but convection through a boundary layer, and is 1 over H. For air, this would be 0.03 watts per meter Kelvin. H is 10 watts per meter square Kelvin. The watts go away. This meter go away with this and comes to the top. Kelvin go away. And I have L is more or less 3 millimeters. So our jacket, if we don't move, is 3 millimeters thick. What if there is wind? For what is called forced convection, we have H is more or less 100 watts per meter square Kelvin. L equals, what would be the thickness of the boundary layer if you're riding your bike? 0.3 millimeters, that's right. And this is a story of why, like, we would use like a fan or something. If they blow air on us, what happens is we make a thinner boundary layer, and that's the reason we lose more heat.